Chemistry, Presentation Speech in English. The Nobel Prize for Chemistry, Speech made by the President of the Royal Academy of Science, translation. One of the most prominent features of physical research in our day is the reciprocal action characterizing physics and chemistry, causing an important discovery in one or other of these sciences almost invariably to affect the sister science. Thus, Lord Rayleigh's investigations concerning the physical properties of certain gases that have just received award gave rise to a whole series of surprising and important discoveries in the department of pure chemistry. Lord Rayleigh having proved the wonderful difference in density existing between atmospheric nitrogen and nitrogen chemically prepared, another British scientist, already well known as an eminent chemist, received permission to cooperate in the continued investigations with the intention of discovering, if possible, the cause of the peculiar state of things previously mentioned. The result of this cooperation was the discovery, made public in 1894, that the air contains a gaseous component, previously unknown, of nearly half as great a density as nitrogen, which explains the higher specific weight of the atmospheric nitrogen. A careful study of the properties of the new gas soon proved beyond all doubt that a new chemical element had been discovered, which, owing to its disinclination to enter into chemical association with other elements, was called argon, the inactive. Not content with having proved the presence of argon in the gaseous envelope of the globe, Lord Rayleigh's chemical cooperator, on his own initiative, devoted himself to searching for the occurrence of argon in the firm crust of the earth. This led him to a new discovery, scarcely less surprising than the preceding. He succeeded in isolating a gas from certain uranitic minerals, which gas in the spectroscope proved identical, not to argon, but to the long sought-for solar element helium, hitherto undiscovered on the globe, the existence of which had first been demonstrated by Janssen, the French astronomer, during a spectroscopic examination of the solar chromosphere in 1868, while making observations on an eclipse of the sun in India. It has subsequently been found that helium is also present in the water of some mineral springs, in certain meteoric stones, and that, like argon, even in a far less degree, it forms a component of the atmosphere of the earth. As soon as the atomic weight of the two new gases had been approximately determined, as 4 for helium and 40 for argon, the energetic scientist, by theoretical reasoning, was led to search for yet another elementary gas, the atomic weight of which should lie between the two preceding gases, and probably be about 20. Having made a great number of fruitless attempts in various directions, he at last obtained an active agent when the problem of making liquid air on a large scale was practically solved. With the assistance of the low temperature which occurs when liquid air evaporates, -200 degrees and still lower, he was able to obtain considerable quantities of liquid argon without any great difficulty, and both by fractional distillation thereof, as also by direct fractioning of liquid air, in the more freely volatile fractions he succeeded in demonstrating the sought-for element which was called by him neon, the new. Nor was this all. In the less freely diffused fractions of the air he almost simultaneously discovered two new elements, both gaseous at ordinary temperature, of greater density than argon, the existence of which said gases he had predicted, though with rather less certainty, and for which he proposed the denominations krypton, the hidden, and xenon, the strange. These gases occur in the air but sparingly as a rule, for while argon forms nearly 1/100th of the volume of the air, neon occurs only as 1 to 200,000th, helium as 1 to 2 millionth, krypton as 1 millionth part, and xenon only as about 1/20 millionth. This, more than anything else, will enable us to form an idea of the vast difficulties which attend these investigations. In spite of all obstacles, however, it has not only been found possible to isolate the new elements, but also to study their peculiarities with an accuracy which enabled their place to be determined in the periodic system of the elements. It has been demonstrated that the 5 new gases, or noble gases, as they are often called, form a natural family of elements which by the absence of electric polarity is strictly differentiated from all elements previously known, filling a void in the periodic system hitherto existing between the highly negative halogens and the highly positive alkali metals. The discovery of an entirely new group of elements, of which no single representative had been known with any certainty, is something utterly unique in the history of chemistry, being intrinsically an advance in science of peculiar significance. The more remarkable is this advance when we recollect that all these elements are components of the atmosphere of the earth, and that, though apparently so accessible for scientific research, they have for so long a time baffled the acumen of eminent scientists, who from the time of Scheele, Priestley, and Lavoisier to our own day have been occupied in determining the chemical and physical properties of the air. The discovery, however, signifies far more than the simple addition of 5 new elements to the 70-odd that are already known. This to no slight degree owing to the indifferent character of the new gases, which certainly renders their study very difficult, but at the same time places them in a very peculiar position among the other elements. In spite of repeated and indefatigable endeavours, it has been found impossible in any authenticated case to induce chemical combination either with one or another or with other known elements. Such a total indifferentism among elements was previously unknown. Indeed, it was pretty generally believed that the power of entering into chemical reaction was a fundamental attribute which, though in a higher or lower degree, characterized all the elements. The discovery of the noble gases has removed this impediment to our knowledge, widened our far too narrow view of the nature of the elements, and for this reason, even from a theoretical aspect, is of special interest. This interest has of late been still further heightened by the observation that the spectral lines of helium appear in the emanations from radium, that very puzzling element, an observation which may bear fruit in results for science, the full extent of which it is now impossible to foresee. The scientific triumphs denoted by the discovery of the noble gases are easily described, though they have not been acquired without great toil, being not merely a combination of fortunate circumstances, but the result of a well-planned, persevering, and tiresome work. The man who has opened these new realms of nature to science, and to whom the Royal Academy of Science has decided to award the Nobel Prize in Chemistry for the present year, is Sir William Ramsay, Professor at the University College, London. End of section 5. Recording by Sean Michael Hogan, St. John's, Newfoundland, Canada. 6. Chemistry, Biography in English. Sir William Ramsay. Born in Glasgow on October 2, 1852, Sir William was a Scot by birth, his paternal uncle being the geologist Sir Andrew Ramsay, his grandfather an eminent man in the department of practical chemistry. From 1866 to 1870, William Ramsay studied in his native town, then went to Germany where he worked in Fittig's laboratory at Tübingen, 1870 to 1872. While there, he obtained his degree as Doctor of Philosophy by a treatise on orthotoluic acid and its derivatives. Later on, he was made an honorary doctor of Dublin University. On his return to Scotland, he became assistant in chemistry at the Anderson College in Glasgow in 1872, 2 years later obtaining a corresponding position at the university of the same town. In 1880 he was nominated Professor of Chemistry at the University College, Bristol, where from 1880 he also acted as principal, while in 1887 he was called to fill the chair in inorganic chemistry at the University College, London, which post he still holds. Ramsay's earliest works are in the department of organic chemistry. Besides his doctor's dissertation, about this period he published work on picoline, and, in conjunction with Dobby, on the decomposition products of the quinine alkaloids, 1878-79. From the commencement of the 80s he was chiefly active in the department of physical chemistry, his many contributions to this branch of chemistry being mostly on stoichiometry and thermodynamics. To these must be added his investigations carried on with Sidney Young on evaporation and dissociation, 1886-89, his paper on the molecular weight of metals, 1889, where he proved that the molecules of most metals in solution consist of a single atom, etc. Finally, in the special department of inorganic chemistry, Ramsay has carried out his most celebrated investigations, most particularly those for which he received the Nobel Prize. Still earlier, 1885-90, he published several papers on the oxides of nitrogen. Then followed the discovery of argon, and of the other so-called noble gases occurring in the atmosphere, helium, neon, krypton, and xenon. Led to the conclusion by different paths, and at first without working together, both Lord Rayleigh and Sir William Ramsay succeeded in proving that there must exist a previously unknown gaseous matter in the air. They then tried to solve this problem, certainly each in his own laboratory, but communicating almost daily as to the result of their investigations, until at the meeting of the British Association at Oxford in August 1894, they deemed they could give a brief account of the discovery of argon. While seeking for sources of argon in the mineral kingdom, in 1895 Ramsay discovered helium. Guided by theoretical considerations founded on Mendeleev's periodic system, he then methodically sought for the missing links in the new group of elements, and found, 1898, the above-mentioned other noble gases. When carrying on the necessary experimental work, he was assisted by several younger scientists, more especially Morris B. Travers. Yet another incentive to research, the vast importance of which it is impossible to foresee, was given by Ramsay in conjunction with F. Soddy, by his discovery of the occurrence of helium in the emanations of radium, 1903. Ramsay's most important discoveries and works, for which he was awarded the Nobel Prize, are published in the following issues. Argon, a New Constituent of the Atmosphere. Proceedings of the Royal Society, Volume 59, pages 265 to 287, in conjunction with Lord Rayleigh. The Discovery of Helium. Chemical News, Volume 71, page 151. Helium, a gaseous constituent of certain minerals. Part 1, Proceedings of the Royal Society, Volume 58, pages 81 to 88. Part 2, Volume 59, pages 325 to 330. The Position of Argon and Helium among the Elements. Boyle Lecture, Chemical News, Volume 73, page 283. Helium and Argon. Part 3, Experiments which show the inactivity of these elements. Proceedings of the Royal Society, Volume 73, pages 53 to 56, and Chemical News, Volume 73, pages 259 to 260, together with J. N. Colley. On the Companions of Argon. Proceedings of the Royal Society, Volume 62, pages 437 to 440, and Chemical News, Volume 78, pages 1 to 2, together with M. Travers. The recently discovered gases and their relation to the periodic law. From the Smithsonian Report for 1898, pages 267 to 276. The Aurora Borealis. Papers of the Greenock Philosophical Society, 21 pages. An attempt to estimate the relative amount of krypton and xenon in atmospheric air. Proceedings of the Royal Society, Volume 71, pages 421 to 426. Experiments on radioactivity and production of helium from radium. Proceedings of the Royal Society, Volume 72, pages 204 to 207, and Chemical News, Volume 88, pages 100 to 101. With regard to the scientific honors which, besides the Nobel Prize, have been awarded to Ramsay, mention may be made of the Davy and Longstaff medals, while America awarded him the Barnardo Medal and a prize of $5,000 from the Smithsonian Institution, France a prize of 25,000 francs, and Berlin in 1903, together with Moissan, the A. W. Hoffman Medal in gold. End of section 6. Recording by Sean Michael Hogan, St. John's, Newfoundland, Canada. Heat at constant volume to that at constant pressure was measured in the year 1892 with the assistance of Dr. E. Perman, but an account of the results was not published till 1896. The method employed, that of Kundt and Warburg, gave adiabatic curves for ethyl ether, both in the liquid and the gaseous state. Before leaving Bristol, I had carried out some experiments in connection with the combination of gaseous nitrogen with hydrogen and with oxygen, with the aid of platinum as a catalyzing agent. The results of the search were negative and were not published. But I must have read the well-known account of Cavendish's classical experiment on the combination of the nitrogen and the oxygen of the air at that date, for in my copy of Cavendish's Life, published by the Cavendish Society in 1849, opposite his statement that on passing electric sparks through a mixture of nitrogen with excess of oxygen, he had obtained a small residue, amounting to not more than 1/125th of the whole, I find that I had written the words, "Look into this." It must have been the latent memory of this circumstance which led me, in 1894, to suggest to Lord Rayleigh a reason for the high density which he had found for atmospheric nitrogen. With the discovery and properties of argon I do not propose to deal. Hence I pass on to the discovery of terrestrial helium and of its congeners. One of the most characteristic properties, or rather want of properties, of argon is its forming no compounds, a circumstance which led to the choice of its name. It had been observed by Dr. Hillebrand, one of the chemists to the Geological Survey of the United States, that certain minerals, notably those containing uranium, gave off a gas when heated with dilute sulfuric acid. I was told recently that the investigators of this gas observed in its spectrum certain unknown lines, but they were deterred by the criticism of their colleagues from attaching much importance to the observation. The spectrum contained the usual bands of nitrogen, and they contented themselves with chronicling this observation. The evolution of this gas from a rare mineral struck me as likely to afford a clue to the direction in which to seek for a compound of argon, for it appeared not unlikely that the gas examined by Hillebrand might turn out to be argon mixed with nitrogen. But on examining the gas, a brilliant yellow line was observed, nearly, though not quite identical in position with the double line of sodium. Reference to a list of spectrum lines established the coincidence of the new line with a line which had been first observed in the solar spectrum by M. Janssen during an eclipse of the sun, to observe which an expedition had been sent to India in 1868. It was suspected by Frankland and Lockyer that the line was due to hydrogen, but no means was found of causing that element to show such a line. They therefore came to the conclusion that it must be due to the presence in the solar atmosphere of an element unknown on the Earth, and they gave it the name helium to suggest its solar origin. Shortly afterwards, Langlet, working in Cleve's laboratory, discovered helium independently. Helium, like argon, is a gas, sparingly soluble in water, withstanding the action of oxygen in presence of caustic soda under the influence of the electric discharge, as well as of red-hot magnesium. Like argon, the ratio of its specific heat at constant volume to that at constant pressure shows it to be a monatomic element, the atom and the molecule being the same, and its density was found both by Langlet and myself to be nearly 2. It is, therefore, the lightest gas known, with the exception of hydrogen. These properties in common made it evident that helium and argon belong to the same natural family, and it was also obvious that there must exist at least 3 other elements of the same class. This is evident on inspection of the periodic table, where the following elements are in apposition: hydrogen, atomic weight 1, helium 4, lithium 7, fluorine, atomic weight 19, unknown 20, sodium 23, chlorine, atomic weight 35.5, argon 40, potassium 39, bromine, atomic weight 80, unknown 82, rubidium 85, iodine, atomic weight 127, unknown 130, cesium 133. In the belief that these elements would be discovered, I predicted in the presidential address which I gave to the chemical section of the British Association when it met in Canada in 1897, the discovery of a new element. I thought it well to be on the safe side, and the necessity of an element with the atomic weight 20 was evident, although it might have been maintained with almost equal probability that 2 other awaited discovery. Dr. Travers, then my assistant, now my successor in the Bristol chair, was kind enough to lend his help in the search for this new gas. We made a plan of campaign which was strictly adhered to, and which resulted in success. First, we investigated the gases evolved from every mineral which we could obtain, and the authorities of the British Museum were so good as to place a large number of specimens at our disposal. Second, various meteorites were heated, and their gases examined spectroscopically, after removing those gases which could be induced to enter into combination. Third, Dr. Travers and I made an expedition to Cauterets in the Pyrenees, and I collected gases from the hot springs in Iceland, and in addition, gases from various English and Scottish mineral springs were investigated. Fourth, about 4 liters of helium were prepared from Fergusonite, and this gas was fractionally diffused during about 3 months, in the hope of obtaining heavier fractions, which might contain the looked-for gases, for they would certainly betray themselves by their spectra if present. Fifth, a similar set of diffusions was carried out with argon, though not to the same extent, for by that time we had other facilities. Sixth, about 15 liters of argon was prepared, with the intention of submitting it to fractional distillation, for in the meantime Dr. Hampson was working at his excellent machine for liquefying air, and he kept me informed of his progress. The carrying out of this long program occupied me a large part of the years 1896 and 1897. The 15 liters of argon was prepared after Christmas, 1897. The results of these attempts to detect a new gas may be disposed of in a few words. First, those minerals which contain the elements uranium and thorium yielded helium in small quantity. But in no case were we certain of a new line in the spectrum of that element, with which, it may be remarked, we became almost painfully familiar. The only mineral which yielded a gas containing argon was malachone, a silicate of zirconium. Second, only one meteorite from Augusta County, Virginia, USA, gave inactive gases. Both argon and helium were found. Third, the Cauteret gases contained both helium and argon, but although they were fractionated, nothing new could be discovered. It has since turned out, however, that the water from the Bath Springs contains neon. Fourth, the diffusion of helium yielded a small residue in which only the familiar lines of argon could be detected. But again, the use of liquid hydrogen has made it possible to cool a large quantity of helium to a very low temperature, and the condensed portion has been found to exhibit the spectrum of krypton. Fifth, the diffusion of argon resulted in the accumulation of two fractions, one of which was slightly more dense than the other, and this, although we now know that the difference must have been due to errors of experiment, afforded us at the time a little encouragement. While the 15 liters of argon was being purified, Dr. Hampson had succeeded in perfecting his machine, and he placed at our disposal about a liter of liquid air. After playing with it, so as to familiarize ourselves with its properties, there remained in the vessel about 100 cubic centimeters. I suggested that we should allow this portion to evaporate almost entirely away, and that we should collect the last 10 cubic centimeters by allowing it to boil off into a gas holder. This was done, and after removal of oxygen and nitrogen, there remained 26 cubic centimeters of a gas which showed, besides the spectrum of argon, a bright yellow and a bright green line, of wavelengths 5571 and 5570.5 respectively. Although the density of the new gas, which we named krypton, or hidden, was found to be only 22.5, we conjectured that, when purified, it would turn out to be 40 times as heavy as hydrogen, implying the atomic weight 80, for our early experiments established the fact that, like argon, its molecular and atomic weights were identical. An account of this discovery was communicated to the Royal Society on June 3, 1898, and no time was lost in examining the argon by liquefaction and fractional distillation. On June 13th, we were able to announce that the lower boiling portions of the 15 liters of argon contained a gas which we called neon or nu. It showed a spectrum characterized by a brilliant flame-colored light, consisting of many red, orange, and yellow lines. A preliminary determination of its density yielded the number 14.7, and after one fractionation, the density decreased to 13.7. We were at this time misled in supposing that a second gas was present, showing a spectrum different from that of argon, but possessing almost the same density. We regarded it as bearing to argon the same relation as that of nickel to cobalt, and we christened it metargon. This gas subsequently turned out to be argon in the main, but to contain carbon monoxide, owing to the use of an impure specimen of phosphorus containing carbon in removing the oxygen, but it gave us a great deal of trouble to make sure that it was not a new individual. Callas, working in my laboratory, and Schlüssing in Paris, had independently determined the amount of argon in the air. They found almost identical numbers, 0.01183 Schlüssing and 0.01186 Callas part by volume in 1 part of atmospheric nitrogen. The separation of the lighter and heavier gases from argon gave occasion for a redetermination of the density of argon using a pure sample. While the crude argon prepared by withdrawing the nitrogen from atmospheric nitrogen by the electric flame was found to have the density 19.94, and by the use of red-hot magnesium 19.941, the density of the purified sample gave the number 19.95. The refractivity, however, shows a greater difference, for the admixture of helium and neon in the crude sample lowers the refractivity from 0.9665 for the pure gas to 0.961 or 0.960. In September 1898, the discovery of another gas was announced. It was separated from krypton by fractionation, and possessed a still higher boiling point. We named it xenon, or the stranger, and during the next 2 years Travers and I prepared a larger quantity of these gases and purified them by fractionation, while Bailey erected an apparatus for the accurate determination of the wavelengths of their spectral lines. We procured from the Bryn Oxygen Company one of Hampson's air liquefiers, and from the Whitehead Torpedo Company one of their compressors, The latter was driven electrically by means of a 5-horsepower motor. The motor has since been replaced by a more powerful one, but the compressor and liquefier have given no trouble and still work as satisfactorily as when first purchased. In 10 minutes after starting, without any preliminary cooling, liquid air begins to run, and the yield is over a liter an hour. By help of this machine, air was so fractionated as to furnish portions rich in the gases which we wished to investigate. The process was as follows. The air liquefier furnished a supply of liquid air. The gas escaping from the liquefier consisted largely of nitrogen. This mixture was liquefied under pressure in a bulb cooled by the liquid air boiling under reduced pressure. When the bulb had been filled with liquid nitrogen, a current of air was blown through the liquid until some of the gas had evaporated. That gas was collected separately and deprived of oxygen by passage over red-hot copper. It contained the major part of the neon and helium present in the air. The remainder of the nitrogen was added to the liquid air used for cooling the bulb in which the nitrogen was condensed. Having obtained a considerable quantity of this light nitrogen, it was purified from that gas in the usual manner, and the argon containing neon and helium was fractionated. By fractional distillation, it was possible to remove the greater portion of the helium and neon from this mixture of gases, leaving the argon behind. The air used in these fractionations was allowed to evaporate in vacuum vessels during the operations, but care was always taken to save the dregs and collect them in a gas holder. In this way, a large quantity of the heavier portions of the air was accumulated. We estimated the quantity of air thus concentrated as not less than 30 liters of liquid. After removal of oxygen and nitrogen, the argon was separated for the most part by fractional distillation, and the residue of crude krypton and xenon purified by repeated fractionation. While krypton has a considerable vapor pressure at the temperature of boiling air, the vapor pressure of xenon is hardly appreciable. Hence their separation, although tedious, presented no particular difficulty. It was otherwise with neon. It soon transpired that the neon was contaminated with helium, and many attempts were made to effect a separation before they were crowned with success. Among these was fractional solution in oxygen, followed by a systematic diffusion of the two gases, but it was not found possible to raise the density of the neon above the number 9.16, and its spectrum still showed helium lines. Neither neon nor helium can be liquefied by cooling with liquid air, and it soon became evident that without the aid of liquid hydrogen, no further progress could be made. Dr. Travers therefore undertook, with the assistance of Mr. Holding, the laboratory mechanic, to construct an apparatus for liquefying hydrogen, and in doing this he had to start from first principles, for no account had been published of the process. After 2 months' work, a machine was produced, in which the hydrogen, after preliminary cooling with liquid air, entered a chamber in which air boiled at low pressure, at a temperature of -205 degrees. This degree of cold was sufficient to carry it below the critical temperature for the development of the positive Joule-Thomson effect, so that when it was allowed to expand, after traversing a regenerative coil, it ran out in the liquid form. With this powerful agent to help us, the separation was effected in less than an hour. The mixture of helium and neon, compressed into a bulb cooled with liquid hydrogen, deposited the neon in the liquid, or more probably in the solid state. The vapor pressure of liquid neon at that low temperature is not more than 17 millimeters of mercury, while helium is permanently gaseous. It was easy, therefore, to purify the neon from helium, though it would have been a difficult task to purify the helium from neon. That these are all monatomic gases was proved by determining the ratio of their specific heats by Kuntz's method, and accurate determinations were made of their refractivities, their densities, their compressibilities at 2 temperatures, 11.2 degrees and 237.3 degrees, and the vapor pressures of argon, krypton, and xenon were determined, as well as their volumes at their boiling points in the liquid state. The critical temperatures and pressures of the last 3 were also determined. It may be stated in general terms that these gases show a regular gradation of properties from helium to xenon, and that they fill the gaps in the periodic table below and above argon with the atomic weights neon 20, krypton 82, and xenon 128. The amounts of neon and helium in air have since been measured. The former is contained in air in the proportion of 1 volume in 81,000, the latter 1 volume in 245,000. The amounts of krypton and xenon are very much smaller. Not more than 1 part of krypton by volume can be separated from 20 million of air, and the amount of xenon in air by volume is not more than 1 part in 170 million. In June 1903, Mr. Bailey published an account of his determination of the wavelengths of the lines in the spectra of neon, krypton, and xenon, photographed by help of a concave Rowland's grating of 10 feet radial curvature. In all, the positions of 2,400 lines were accurately measured. The discovery that uranium emits rays, capable of discharging an electroscope and impressing a photographic plate, made in 1896, was followed by the separation from pitchblende, the chief ore of uranium, of that remarkable element radium, by Madame Curie in 1898. In 1899, Giesel and Meyer and Schweidel in Germany and Austria, and Becquerel and P. Curie in France, found almost simultaneously that certain rays from radium, later called the beta rays, could be deviated by a magnetic field, and these rays have since been shown to be identical with the cathode rays, proceeding from the cathode of a highly exhausted tube. These rays possess great penetrating power, for they pass through considerable thicknesses of metal without absorption. It was not till 1900, when Madame Curie threw out the suggestion that the alpha rays, which were stopped by small thicknesses of metal or glass proceeding from polonium, might be of the nature of small particles projected with great velocity, but which lost their energy in passing through matter. Strutt, in 1901, made the same suggestion for the alpha rays from radium, which are not deviable except in a very powerful magnetic field. Rutherford, in 1902, determined the deviation of these rays in a known magnetic field, and also in an electrostatic field, and arrived at an estimate of the value for the ratio of mass to electric charge for each particle, and on the supposition that the charge is the same as that carried by an ion of, say, hydrogen, he arrived at an estimate of the mass of each particle. Calculation showed it to approximate to twice that of an atom of hydrogen. After Schmidt and Madame Curie's discovery in 1898 that compounds of thorium and the minerals containing it possessed properties similar to those of uranium, Owens found that the power of discharging an electroscope could be greatly modified by blowing a current of air over the specimen. And in 1900, Rutherford proved that this was due to the fact that the thorium evolves a radioactive gas. This gas was investigated by Rutherford and Soddy, who made numerous experiments with the view of elucidating its chemical nature. They found that it resisted the action of all oxidizing agents, and also of magnesium at a red heat. From these observations they concluded that the emanation is an inert gas, analogous in nature to the members of the argon family. The emanation was found to decompose after a few minutes, losing its radioactivity, while it evolved rays, a large proportion of which was of the kind termed alpha, and bearing in mind that the mass of the alpha particle was probably of the same magnitude as that of helium, and also recalling the observation that those minerals which yield helium, when heated, almost invariably contain uranium or thorium or both, they continued, the speculation naturally arises whether the presence of helium in minerals and its invariable association with radium and thorium may not be connected with their radioactivity. Mr. Soddy came to work in my laboratory in the spring of 1903, and we at once began to investigate the properties of the radium emanation, for its life is so much longer than that of the thorium emanation, in the proportion 463,000 to 87, that it is possible to deal with it by ordinary physical methods. The emanation from about 60 milligrams of radium bromide was collected during 8 days. It was introduced into a minute measuring tube, and its volume determined. It was found to be a self-luminous gas, obeying Boyle's law, and its volume slowly contracted during 4 weeks, until at the end of that time only the smallest visible bubble remained, which nevertheless still appeared as a brilliant speck of light, and on heating the tube which had contained the gas, a gas was evolved from the walls, possessing 3½ times the volume of the emanation, which showed the spectrum of helium. It had doubtless been projected with a velocity considerable enough to cause the molecules to embed themselves in the glass of the tube, from which they were expelled at a red heat. Other experiments show that it is easy, by heating a radium salt which has been prepared for some time, to expel the helium which has accumulated. This result has been repeatedly confirmed, not only by Mr. Soddy and myself, but also by other observers. Much work remains to be done on these emanations. In conjunction with Dr. Colley, my colleague, the spectrum of the radium emanation has been mapped. It resembles, generally speaking, those of the inert gases, and although its density has not been accurately determined, it appears to be approximately 80, which would imply a molecular weight of 160, and if it is a monatomic gas, Its atomic weight would also be 160. It might then be an unstable member of the argon family. There is a vacant place for an element with atomic weight about 162. The rate of diffusion of the thorium emanation is even less satisfactorily determined, but it also appears to be high. It is still more unstable, and might perhaps have the atomic weight 215, for which there is a gap. And it is not inconceivable that the still more unstable emanation from the matter named actinium by de Bierne and emanium by Giesel might be found to possess an even higher atomic weight than uranium. Judging by the phenomenon of brilliant illumination, when a preparation of emanium is held above a screen of zinc sulfide, the impression is formed that a very dense matter is falling down on the screen. But I am leaving the regions of fact, which are difficult to penetrate, but which bring in their train rich rewards, and entering the regions of speculation, where many roads lie open, but where a few lead to a definite goal. I will therefore content myself with thanking you for the kind attention with which you have listened to my discourse. End of section 7, recording by Sean Michael Hogan, St. John's, Newfoundland, Canada.
Please like and subscribe and click the bell icon to get new video updates.